Dear participants, in this session we will be seeing that how a stepper motor can be driven using Uno platform. You see here, this is a very simple demonstration board where we have connected. This is a stepper motor. This is a typical 6-wire stepper motor that needs 12 volt for its operation. This is the driver circuit. You can see very simply, this is a ULN 2003 driver. Here is the Arduino Uno board, and the Arduino Uno board actually supplies 4 digital signals to the ULN inputs, and respective outputs are connected to the stepper motor. These LEDs are connected to indicate the different patterns, signal patterns that we need to supply to the stepper motor in order to make it operational. Now see here that since this stepper motor is a 12 volt motor, we have an external input ready to which we connect a regular 12 volt supply. For this particular experiment, we will be using such type of SMPS supply. So that will be used here. We can very simply connect it, and you can see that these LEDs are in operation. Because of the glare we cannot find actually, I will try to show. You can see here that okay, it's not visible, but 2 LEDs are right now working among the 4 LEDs, and 2 LEDs are off. So now you can see, I have just tried to show you that actually during operation the pattern of the LEDs change. A certain pattern is required, that we have studied in great detail during our theory sessions, that what pattern we have to actually feed to the stepper motor to make it rotate clockwise or in anti-clockwise manner. So initially I will just concentrate on discussion through which we will understand that how to connect the stepper motor, or rather how the different wires, because whenever you are handed with a stepper motor with its 6 wire, it's really a very confusing state that how to connect these 6 wires to the supply and different pins of the driver. The question arises that why driver is required. You see that stepper motor coils, they have to be energized in particular pattern to make it operational. Now these coils, they actually draw a very significant amount of current. You can see this is one of the stepper motors that we had extracted from one old printer. So this motor is a very miniaturized motor and it does not draw a significant current. It requires some current that is less than 300 milliampere per phase, that means per coil. However, you can find stepper motors which may require 1 ampere per phase or 1.5 ampere per phase, even more than that. Therefore, you cannot expect that the Arduino will be supplying necessary current to drive the stepper, and therefore you need a current, you can say booster, you can say amplifier. However, in this case, we have used a Darlington pair IC. So this ULN2003 is a Darlington driver, and that simply takes care of the high current that we have to negotiate while driving a stepper motor through any low power logic circuit. It can be Uno, it can be some other controller or processor. Now here you can find, if you look closely, you may please find that there are 5 pins. 1, 2, 3, 4 and 5. Remember that amongst these 5 pins, one pin is connected to common. As per the ULN terminology, it is common. In our case, we will be connecting 12 volt supply to it, and rest of the pins are connected to the coil terminals of the stepper motor. So right now you can see the terminals are not connected. Now using this relematic connector, we can complete the connection. Now the point is, what is the necessity of this particular terminal bridge? It is really not required. You can directly connect the wires. However, in order to understand that how to identify those 6 wires of the stepper motor, I have kept it open like this so that it becomes easy for demonstration. Initially, what I will do, I will disconnect one of the supply terminals. For that, I will be using this shoulder. Yeah. Now you can find that there are 6 wires for this stepper. That very easily means that each of the supply terminals are connected to 2 coils internally. Now the point is here, when I am telling you that this red and this orange are supply wires, fine, it is very easy to listen, but whenever you are handed over with the motor for the first time, you do not know which of them are supply wires. The yellow and green, it can be also supply wire. Normally, the color denominations are given, but if it is not given, it becomes very difficult. So I will tell you the method by which we can do that. Now you may please find that I have put my multimeter for measurement of resistance, and I will keep on just measuring the resistances. You can see here, I will put this orange terminal common, and I will be going for checking the resistance between orange terminal and yellow terminal. You can find it is 131 ohms. Then I will be going for orange terminal and the green terminal. You can see there is no connection. Then the brown terminal. Now you can find that there is absolutely no connection. Then the black terminal. Here you can find again you are having a resistance of 132, 133 ohm. Now see, once this relation is established, now we have to further check the resistance between this yellow terminal and the black terminal. You can find it is 266 ohm, just double of what we had observed in individual cases of yellow and orange and black and orange. Now why this is happening? Here you need to understand that this orange wire, it is connected to a common terminal of the two coils of the stepper motor. It is connected to the common terminal of the two coils of the stepper motor, and the other terminal of those two coils are connected to this yellow wire and black wire. Since it is like that, then when you are measuring the resistance between black and yellow, you are actually measuring the resistance of two coils, and individual resistance can be measured in between the common terminal and the other terminal of the coil. So if this is okay, then we can think of this red wire, brown wire and green wire to have same sort of relation. So let us see this red wire. Let us consider that it to be the common terminal that we need to go for supply. You can see with the green wire it is 133 ohm. With the brown wire it is 133 ohm, and this brown and green it is having 266 or 267 to it, something like that. So yes, whatever we had seen with the orange, yellow and black group, the same relation is established for this red, green and brown group. So now I will make these two supplies common. So I will again solder it here. Done. Now see, let us uh, go for understanding of the driver part. You see that we are using ULN 2003 IC. You can see here, actually this is a 16 pin IC. You can find pin number 8 to be ground and pin number 9, that is the common. You can see these are freewheeling diodes so that any inductive load can be negotiated, and this common freewheeling diodes is the common point to which you have to give either supply or ground depending on the necessity. Whether you are using this pin as a sink or a source, that depends. But right now, my simple question will be that whether this point can act as a source also, that we need to check. That we will understand when we simply look into the actual operation of Darlington. So let us go for that. Before that, we will see the work of a transistor as a switch. That will make our understanding further clear. You can see here that we have connected the load in between supply and collector. Now we are giving a low current signal to the base, and because collector current is related to the base current with beta, that is forward current gain, we can very easily envisage that whatever the base current is, we will get an amplified value in the collector current, because collector current is equal to beta into base current. This beta is having higher value, maybe 100, 250 or 300, like that. Now see here, what does this mean? This signifies that with a very low power signal, you can drive a high current load. So if this load requires a heavy current, then you see this circuit goes extremely handy. This is what is called an open collector connection, because you can see your collector is open to the source and in between you actually connect the load. Now remember that this is the particular configuration in which the transistor works as a switch, and definitely amplification is happening. Now let us try to see what is Darlington then. So you can see, using a single transistor also you can achieve amplification. Now let us look into the Darlington configuration. Here we use actually two transistors. So the amplification is due to this dual stage action. We supply a base current. Because of that, we supply the base current to transistor 1. We get a collector current. This collector current here, it is designated as IC1. Now you see, this IC1 is definitely greater than base current. Because of the beta factor, I will take it to be beta 1, because it is of transistor 1. Now most beautifully you can find that whatever collector current it is flowing through the transistor and coming to the emitter, that becomes the base current for transistor 2. So base current for transistor 2 is already an amplified form of the applied base current, and because of the beta gain or forward current gain of transistor 2, you get a further amplification at the collector current. So here if we connect a load, this particular Darlington configuration, it will be able to negotiate a higher amount of load current. So this is basically the operation of a Darlington. So now you can find that here this emitter has to be connected to ground and this collector has to be connected to supply. Now let us look into the internal configuration in ULN IC. You can find here, this is the ULN, and here you can see we are giving the input at these points: I1B, 2B, 3B, 4B, 5B, 6B and 7B. That means we have got 7 inputs that are very beautifully TTL, and both TTL and CMOS compatible. Now each input is having one corresponding output. So that is 1C, 2C, 3C, 4C, 5C, likewise. Now you see, in case of this 2003, each Darlington pair, or each Darlington driver, they can handle up to 500 milliampere of current. That is quite significant. And you have to put your input on this side. Corresponding output is just the opposite pin. If you need 8 input or 8 Darlington channels, you can go for this ULN 2803. That is another IC of this family. Now you see here that this is the view of one channel. You can find that here we have to connect the VCC. You can see here it is clearly written VCC here. So we have to connect the VCC in this terminal, and the output has to be connected to this terminal. Now you can see this output. This is output. So output has to be connected so that the transistor can sink current to ground. Therefore, what we had earlier decided, that in this pin number 9, we can connect either VCC or ground, that concept is not correct. You have to connect the common VCC here, and the load you have to connect in open collector format. That is, these points, pin number 16, pin number 15, pin number 14, 13, 12 and 11 and 10, they will all be acting in syncing modality. So deliberately I had put this debate so that we can remember this point very well. Now the circuit here is very easy. You can see that we have used 10 digital pins of Arduino to be connected, extremely sorry, 4 digital pins, 1, 2, 3 and 4 digital pins of Arduino, that is connected to 4 inputs, 1, 2, 3 and 4. And that is finally given to the output, corresponding outputs. These are the coil terminals 1, 2, 3 and 4. These are the coil terminals that are connected to the coils. And this yellow pin, this is connected to this common pin, that is pin number 9 of the ULN. And we have connected this, you can see this is for supply. One pin is for supply and other pin is for ground. You can see very easily. One pin is for supply, the other pin is for ground in this driver circuit that we have connected. And here we are getting actually 12 volt. That 12 volt we have given to the stepper. So that's all about the circuit. It's very simple. We have already discussed this circuit in our theory coursework. Now we have to remember that in order to rotate the stepper motor, we need to provide signal to each coil in a particular pattern. So that I have already fed to the Arduino and we will check the operation. So I will give the 12 volt supply to the board. Now you can see the stepper is not operating yet because the Arduino is not connected. Now I have powered the Arduino and you can see this is counterclockwise rotation. As you can see, the pattern is also changing at the LED side. Now deliberate delay is given. Now you can see the stepper is rotating in clockwise direction. So this is the basic operation, Now we will go for elaborating the program. Here you see that if you get into the library, you will find that there is a library for the stepper itself. You can see this is the library for the stepper, but we have not used here the library. We have simply given signals to the coils to operate the stepper. Now the program is made in such a manner that we will give a count. For that number of count, the stepper will make necessary steps, that much number of steps rather, in the anti-clockwise direction. It will stop for a while, might be it is for 5 seconds, and then it will again make the stipulated number of steps in clockwise direction. So this is the basic objective of this program. Now you see here this program can be written in many formats. You can use very less number of lines to accomplish the same task. However, here I have deliberately make an elaborative view of the program so that we can understand the operation of the stepper. So here we have first declared the pins, pin number digital pin 1, 2, 3 and 4 which are connected to the coils. Then one I has been defined, it is actually the count. Now let us go for the setup part. One important thing that I would like to say you, that the entire program now is working in the setup part. So it will run only once. Had I not done that, you could have found that the stepper is continuously rotating. Then I would not have been able to show you the steps, the number of steps it is traversing and then it is stopping. Now here one important point that I wanted to show you, that normally we do not connect a position feedback for the stepper. Velocity feedback can be there because you see we are not that interested with the velocity of the stepper, but stepper is actually used for positioning purpose. Okay, positioning an object or positioning a turntable like that. Now you see, whenever you purchase a stepper motor, that comes with one specifications, angle per step. So you know that with each step how much angle is going to be traversed. Therefore you can easily calculate angular displacement through the number of steps that the stepper makes. And if you really want that you want to apply this stepper for some linear motion or translational motion, which is very common in CNC machines or likewise operations, you can go for 3D printers. There also you can understand that how much rotation or how many rotation of the stepper motor or how many steps will be making the carriage that is loaded on a ball screw mechanism or lead screw mechanism to what extent. So such mathematical calculations may be made to apply the stepper motors very easily for precision motion control applications. This we have to remember. Now you see what we have done in this setup. We have declared all these pins. You can see here we have named them coil 1, coil 2, coil 3 and coil 4 as output, and then we have written low to each and every pin. So initially they are low. There is a delay of 2 milliseconds. Then a for loop has been used. So you can see here that initial value of the count is 0. It will keep on incrementing until the count is 3. Now you can see that this means that whatever the steps that has been written in between these two braces, these brace, this is one brace and this is another brace, whatever it is written, so it will be repeated for 3 times. Now you can see this particular pattern that has been fed to the coils for anti-clockwise rotation. It is 1100, 0110, 0011 and 1001. Another thing that you need to know, that in between this pattern, this is one pattern that we have given. My task, my assignment to you, you kindly try to develop the hexadecimal format, that what we are actually feeding. Now you can see that each pattern, or we can say the output of each pattern is differentiated with a delay, because if you do not give the delay, then it will be changing the patterns so fast that the stepper might not be able to follow. Now you can definitely change this delay, okay, up to a certain extent, but after that the stepper will start wobbling at very high speed. So if you increase this delay, the steps will be slower. If you decrease this delay, the steps will be faster. Now this particular pattern is for counterclockwise rotation. Now after this counterclockwise rotation is done, for how many steps you can see here. So this pattern will make one step, this pattern will make one step, this pattern will make one step and this pattern will make one step. So there are 4 steps. Whatever the code is written within this brace, that will bring about 4 steps. So here you can see the count is 3. So total number of steps that the stepper will make will be 4 into 3, that is 12. Now I have made all the coils low here to give the system a rest for 5 seconds. Next, the pattern for clockwise rotation has been given. You can see again for a count I is equal to 0 to I 3. So initial value is I is equal to 0. It will increment till the count reaches 3. Again here you have to follow the patterns. This is absolutely important. You can find here high, high, low, low. That means 1, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1 and 0, 1, 1, 0. Again, the assignment is you kindly note down the hexadecimal equivalent. And this, whenever you are working with a stepper motor and you have to give such, I should say, pre-signals to the motor, you have to have this pattern maintained. That you have to remember. Now here again in between each pattern there is a delay. This is so important. Again you can decrease the delay or increase the delay in order to have a control over the speed of rotation of the stepper motor. Again you can find here that it will make 12 steps. So now I will verify the program. I will upload it and I will go for this view. You can see it has started rotating. Now it is given in setup, it is not in loop. So what I will do, I will just go for a reset so that we can just start from the beginning. Step 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13 means I had that minus 1 should be there. Now you see it will be making 12 clock. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Now it stops. So this you can see that you can have such precision positioning capability in your hand when you use a stepper motor. So this was a very basic demonstration of the stepper motor. You can go for several other experiments with that. You may use a simple switch. You can use a SPDT switch. So on one throw the stepper motor may rotate clockwise. On the other throw the stepper motor may rotate anti-clockwise. It may so happen. You can use a potentiometer so that the output of the potentiometer, maybe you can connect the potentiometer to any of the analog pins and that value can be given to the delay. We are writing delay within bracket 1000. So reading of the analog pin can be given to that in place of that 1000. So what will happen in that case? By controlling the shaft of the potentiometer, you can simply control the speed of the stepper motor, speed of rotation of the stepper motor. That is also possible. So there are a number of possibilities. You can also try to use some other driver for the stepper motor. So these are all kept as assignment for you. I hope you will take the interest, and whatever confusions you come across, you kindly put it in the comment box so that we can just get to you with the solutions that you require. Let us keep the discussions open. Thank you.